All right, these are the solutions for free fall 1. I'm going to walk through these problems and through the graphs, and I want us to pay attention especially to what we're going to do with the positive and the negative signs here. That's a really important part of this. So again, as we go through this, I'm going to box our knowns and I'm going to circle our unknowns. And because these are free fall problems, things are going to be a little bit different. So let's just look at this first one and see how it goes. So we got a small child who is holding a water balloon 1.8 meters above his sleeping sister's head. Now, when he releases the balloon, how long will it take to reach her? So the 1.8 meters is our delta y. That's how far the water balloon is going to fall. Then it says when he releases the balloon. Now, the release part is really important. That tells us, one, that he's going to let it fall. So we're in a free fall situation. And two, it tells me that the initial velocity is going to be 0 because he's dropping it, he's releasing it, he's letting it go from rest. So that is, that's going to be a piece of. We're going to have to pay attention to the language here and what that means. And then it's asking how long will it take to reach your head. So as we go through all of this, we're going to have to keep that stuff in mind. So let's kind of write down everything. Let's write down everything we have. So our acceleration, again, we're in a free fall thing, is going to be g, which is 10 meters per second squared, down. And it's important that we recognize that it's down. The next bit that we have is the delta y. The delta y is 1.8 meters. But if we think about what's going to happen, the water balloon is going to start 1.8 meters above the sister's head, and then it's going to fall down and hit her. So the displacement of the ball goes from 1.8 meters to 0. It's down. The displacement of that ball is down. So directionally speaking, the acceleration and the delta y are in the same direction. What that means for me, and one thing we can't forget, is the direction of that delta y. The initial velocity we just talked about is 0 because we're dropping it, because releasing it from rest. And what we want is the time. So we want the equation that has those things in it. That's that third equation, delta y equals v initial t plus 1/2 at squared. We're going to plug in all of our things. So 1.8 is equal to 0 times time plus 1/2 at squared, 10 times time squared. Now, the nice thing about this 0 is it crosses out. We don't need that. So we get 1.8 is equal to 5, 1/2 times 10, t squared. We'll divide both sides by 5. We get 0.36 is equal to t squared. Square root both sides, and that gives us that time is equal to 0.6 seconds. So here's the thing. You don't always have to make gravity negative. You just have to make sure you're consistent across the board. So I left gravity positive. 1.8 is in the same direction. It's also going to be positive. So that's what I'm doing. If I were going to make 10 negative, I would also have to make 1.8 negative. In general, when the problem has things that are just moving down, I don't put in a negative sign. So I also want to find what the final velocity is. So over here, since we have everything else, we'll just use the first equation. V final is equal to V initial plus AT. So V final is 0 plus 10 times 0.6. And that makes the final velocity 6 meters per second. But guess what? That comes out positive. And we said that gravity was down. We said that delta y was down. Those things were both positive. So this final velocity needs to be down as well. They all need to be in the same direction. And that makes sense. If I drop a water balloon on somebody's head, it's going to be moving down when it hits their head. Now, when we make the graphs, up is still up and down is still down. So when we make the position graph, our y is going to start off at 1.8 meters, and we're going to fall down. And we're going to start off at rest, so I'm going to have a 0 slope at the beginning, and we're going to speed up, so the slope's going to increase and get steeper. And then for the velocity, we want to match that. So we start off with a velocity of 0 because we start off at rest. We're falling down. Our final velocity is in the downward direction. So we're going to move into that lower quadrant right there. So this is important. Because G and V final are down, the graphs have negative G and negative V final. The math doesn't have to have the negative signs. It just must, we just must know the direction for everything. That's an important piece. Now, for the next one. Wile E. Coyote, he's a coyote, falls off a cliff that's 80 meters tall. How fast will he be traveling before he reaches the ground? So for this, the word falls is a piece of given information. And it tells me that his initial velocity is 0. 80 meters tall is the cliff that he's falling off of. And then how fast is what I'm after. So we're falling, so my acceleration is gravity, or it's 10 meters per second squared down. One piece of information. The delta y is 80 meters. But we're starting at the top and we're ending at the bottom, so that's 80 meters down. And for both of these, I don't have to put in a negative sign. They're both down. The initial velocity is 0. The final velocity we don't know. So those are my pieces of given information. The equation that has all those in there, and I really want to emphasize this is just like the last unit. I'm just telling you the acceleration. So the equation that has all that in there is the second equation. V final squared is equal to V initial squared plus 2a delta y. So we're going to plug in all our numbers. V final squared is equal to 0 squared plus 2 times 10 times 80. And here's a note I want to make. If we decided to make the acceleration negative, we'd have to make 80 meters negative because mathematically they're in the same direction. And those two negative signs would cancel out at this step. So now we're going to go ahead and calculate everything. V final squared, the 0 part goes away, is equal to 160. I'm going to square, 1600, I apologize. We're going to square root both sides. And that final velocity comes out to 40 meters per second. Now, that's the final velocity. I want to go ahead and do the time. Oh, the other thing. I know that's going to be down because I'm dropping the object, so it's coming straight down. Now, for the time, I'm just going to use the first equation. V final is V initial plus acceleration times time. Plug in our numbers. 40 is equal to 0 plus 10 times time. 40 equals 10t, because that 0 goes away. We're going to divide both sides by 10. And that time comes out to be 4 seconds. Now we want to make the graph. It's going to look the same as the last one because we're falling. So there's my initial position way up there at the top and my time. So we start off at 80 meters. We go down to 0 meters. We start off at rest, so we have to have a flat line at the beginning, and then as we fall, that velocity goes down and gets bigger. So as we move, the slope needs to start off at 0 and go down and get bigger. When we do the velocity graph that goes along with that, again, it falls down. That's why we get that downward thing. And then for the velocity graph, we're going to start off with the velocity at 0, and we're going to move down in our time. All right, so we end up at 40 meters per second down in 4 seconds. And again, these things are down. All right, for our next question, we've got a rocket initially traveling upwards with a velocity of 10 meters per second. So that upward velocity is our initial velocity. That's how fast we're going to begin with, and the rocket burns out. How much higher will the rocket travel before stopping? Now, stopping tells me that my final velocity is 0. So, we've got a lot of things going on here. How much higher is what we're looking for, which is our delta y. So, our acceleration, because there's not going to be anything else acting on it, our acceleration is going to be gravity. It's going to be 10 meters per second squared, and we know that gravity is always down. The next thing that we have is the initial velocity. it's 10 meters per second, but here's the deal. It's traveling upwards. That's 10 meters per second up. Now we have a problem. We haven't seen this yet. When the gravity is down and the initial velocity is up, they disagree with each other in their direction. Mathematically, what that means we have to do is we have to make the acceleration negative because it's in the downward direction. So because that's down and that's up, we have to make the acceleration due to gravity negative. I want you to be very, very specific with your directions so that you know where to put that negative sign, because that negative sign is really, really, really important. Let's go ahead and put the rest of them on. Our final velocity, all right, so sorry, that must make a negative sign. So that final velocity is 0 meters per second. And our delta y is how much higher? That's the piece we don't know. So I want the equation with all of those things. Real quick thing, since we're going to have positive and negative signs, if delta y is positive, my displacement's up. If delta y is negative, that means my displacement is down. So we want that v squared equation. So v final squared is v initial squared plus 2a delta y. We're going to plug in our numbers. So 0 squared is equal to 10 squared plus 2 times negative 10 times delta y. I don't know what delta y is. So make the squareds go away. I have 0 is equal to 100 minus 20 delta y. We'll subtract 100 from both sides, because the 20 delta y is all being multiplied together. That's why we're going to subtract 100 from both sides. It's really important. So the hundreds go away on the right hand side, and it gives me negative 100 is equal to negative 20 delta y. Now we're going to divide by negative 20 to move that over. It crosses out on the right hand side. And then I get that delta y is equal to 5 meters. Because that's positive, it's going to be up. That's important. And for our next little bit, we want to find the time. So we're just going to use the first equation again because we have everything else. V final is equal to v initial plus at. So I have 0 is equal to 10 plus negative 10t. So subtract 10 from both sides there. I get negative 10 is equal to negative 10t. Divide by negative 10 to get rid of that. I get 1 second is equal to my time. So to make our graph for y versus time, we're going to start off at 0. We're going to go up 5 meters. Now, we're starting off with an initial velocity, so we're going to start off with a positive slope, and that velocity eventually becomes 0. So we want that to taper off. All right, that's up at 5 meters. That takes 1 second. Now, for the velocity versus time graph, we're going to start off with a positive velocity. It's going to go down to 0 in 1 second. So there you go. All right, now we have Timmy, top of a deep well. He's going to drop a rock and determines it takes 2.6 seconds to reach the bottom. So he's going to drop the rock. That is a piece of given information. That means our initial velocity is 0. It takes 2.6 seconds to reach the bottom, and I want to know how deep the well is. 2.6 seconds is our time, and how deep is what we're looking for. It's our delta y. So our acceleration is gravity, because we're still falling. That's 10 meters per second squared down. The time is 2.6 seconds. The initial velocity is 0, and I want the delta y. Now, in this case, the delta y is down because we're falling down. The final velocity will be down because, again, we're falling down. And the acceleration's down. So I don't really need to put any negative signs anywhere because everything agrees with direction. I only want to use negative signs if I have a disagreement. So I really want those arrows as much as possible. Now, looking at all of that, we're going to use the third equation. Delta y is equal to v initial t plus 1/2 at squared. So, plugging in all our numbers, we have 0 times 2.6 plus 1/2 times 10 times 2.6 squared. Now, because it's 0 times 2.6, delta y ends up being just, you multiply all that out, 33.8 meters. That's our delta y. And it's down, because everything's down in this question. That's the same sign as g, so it must be down, just like g. Then we're going to go ahead and find the final velocity. We'll use that first equation. Final velocity is initial velocity plus acceleration times time. So that final velocity ends up being 0 plus 10 times 2.6. So the final velocity comes out to be... The final velocity comes out to be 26 meters per second. And then we can graph that, right? So we start off up there and we fall down again for the same reasons. The initial velocity is 0. It's going to become more negative as it goes on. And then start off at 33.8 meters above where we end up. Because it falls down, that's what we want it to look like. Then we're going to do velocity versus time. So my velocity here starts off at 0 and it gets more negative. 26 meters per second down. And it's negative because it's in the downward direction. Alright, last one here. We have a tennis ball launcher shooting a ball straight up with an initial velocity of 30 meters per second. What will the velocity of the ball be after 4 seconds? So let's go through it. We're going to shoot the ball up with initial velocity of 30. And I don't know what the velocity is going to be after 4 seconds. So that 30 meters per second is my initial velocity. Time is 4 seconds. And we're looking for the final velocity of the ball. So the acceleration here, again, is g. We're throwing it up into the air. It's up in the air. There's nothing else acting on it. So the acceleration is g. 10 meters per second squared down. The initial velocity is 30 meters per second, but it tells me that that's straight up. Again, we've got disagreement of signs. When they disagree, the one that points down needs to become negative. So we have that. And the time is 4 seconds. Now I want to know the final velocity. That's my unknown. So I want the equation that has all these things in it. That's the third equation. Oh, sorry, that's the second equation. Now, before we do that, if that comes out to be positive, it's up, and if it comes out to be negative, that final velocity is down. That's really important here. Now, final velocity is equal to initial velocity plus acceleration times time. So the final velocity is equal to 30 plus negative 10 times 4. 30 minus 40, that final velocity comes out to be negative 10 meters per second. This means something. My object was traveling up 30 meters per second. Now it's traveling down at 10 meters per second. So this guy, the object, stopped at the top. It turned around. That's important. We're going to see that in our graph when we do it. And then just to do this, our delta y. Our delta y is going to be, we know everything, right? So just v0t plus 1/2 at squared. So my delta y is 30 times 4 plus 1/2 times negative 10. Sorry about that. Times 4 squared. So delta y is 120 minus 80. Or delta y ends up being 40 meters. Now here's the graph. Since we stop and turn around, that 40 meters is going to happen on the way back down. And we know we stop and turn around because my velocity goes from positive to negative. Another way that we could look at that is the velocity versus time graph. We start off at 30 meters per second and we end at negative 10. So looking at this graph, there is a spot where we stop. So 30 meters per second, end at negative 10. That spot right there, where we cross the axis, is where we stop. The object stops and turns around at this point. The first part of the motion, we're moving forward and slowing down, moving up and slowing down. The second part, we're moving down and speeding up. But that's the place where we stop. If we look at that on the position graph, right there at the very top is where we stop. which stops at that max height. And there we go.